Astrid, the floor is yours.
Thank you for the introduction and thank you all for attending. So I will start with an introduction on OWS. So OWS is a laboratory for biodegradation and compostability testing. It was actually founded in 1988. It was a spin-off of the University of Ghent. And the business that we started with was the design and construction of anaerobic digesters. So we really come from the waste industry. And the first, from there, the laboratory evolved. I believe the first biodegradation test was in 1989. I wasn't around yet. But so we have over more than 30 years of experience. As you can see, we do on the world map, we work for companies all over the world. So it's really export driven. The headquarters is in Ghent in Belgium, and we have quite a large capacity, so over 3,250 reactors. And we have a team of 50, 60 people working full-time on these biodegradation tests. We recently also opened a lab in the US, so it's basically to perform tests of Canadian and American customers. It's not an exact copy of the lab in Ghent, so we only perform certain tests there. But this is quite exciting. So we like to refer to ourselves as a one-stop laboratory for biodegradability, compostability, and environmental testing, meaning that we perform really all tests with regards to biodegradation, compostability, ecotoxicity in all environments, going from soil, landfill, compost. All these tests are covered by ISO 17025. And what is very important about OWS is that we are strictly independent. So we come from the waste industry and we are not involved in product development. So we focus only on testing and of course also creating new test methods, new specification. So we are also very active in standardization and really on all levels. So the European, also American level, but also ISO international level. We are on these tests, we are recognized by all certification agencies on this topic of biodegradation and compostability worldwide. And also, of course, since we've been in this field for 30 years, we've tested a wide range of different samples. So a bit on the standard certification and opportunities. Maarten already mentioned as well. So these are all the different environments. And what I'd like to start with now is really the managed end-of-life options. So where we will really put products in there as like intentionally, like composting, but also biogasification. So biogasification is where we will treat organic waste to create, and biogas will be created. So you get energy production through the treatment of household waste. Compost, on the other hand, there we put in energy, so we don't create energy. So a little bit on the different standards. As you can see, for industrial compostability, we have several standards on the different levels, so the international level, European, American, etc. They are 90 to 95% identical, but there are some differences, and I will elaborate on that in the next slide. For home compostability, we have an Australian standard, also a French one, and there is also a European one under construction on carrier bags. So only carrier bags are targeted there. Maybe as well for the biogasification, there is currently no standard, and there is a demand for it to be created. This because, of course, through the biogasification, you have energy production. So it is getting more and more important, and that's also in the future, it will likely be created, and OWS is also working on that. Currently, there is no standard available. So a bit on the differences between the standards on industrial compostability. So for instance, for heavy metals, there are small differences. Some, depending on the standards, certain metals need to be analyzed, but also the limits can differ a bit, but that's relatively small. The largest difference is in biodegradation and toxicity. For instance, for biodegradation, certain standards require constituents between 1 and 10 or 1 and 15% to be tested separately. And then, for instance, that's the case for the ISO, for AS and ASTM. For toxicity, like plant toxicity is always required, but certain standards also require additional earthworm toxicity testing. It's also important to know that, of course, these standards, they are not fixed, so they are revised every few years. And of course, the requirements can change. So now EN 13432, the European standard, is up for revision, and it might be that they also will incorporate like the requirement that 1 to 10%, for instance, needs to be tested separately for biodegradation. These are, so you have the standards on one hand, and then you also have the certificates. So the certificates are based on these standards, but they can also add additional requirements. And for instance, they also have more rules for bylaws, like special products that need to be tested or certified. I would say the most known logos on industrial compostability are these ones. So the and OK Compost Industrial are based on the European standard EN 13432. And for home compostability, these are the main known logos. So for which products is compostability and biogasification a good option? Of course, think about products for sure like tea bags and coffee capsules, because they bring in additional organic matter to the compost facility, but also products that are filed with organic waste, with food waste, because they're difficult to recycle. Then you also have environments like open water, soil, marine, where it's not the goal to intentionally put products there after their usage, but it's like products end up there because they are used in that environment or through litter. So for these products, also biodegradation can be an added value, but of course it should never be a license to litter just because it is biodegradable in that environment. A little bit, so for biodegradation in soil, you have a test specification on mulch films. The goal is really that mulch films can be plowed in after the season, because it's difficult sometimes to take it back from the land, and also it has a lot of sand and on it, so it's also not easy to recycle. And you also have, for certificates, you have also 2 certificates. There, I will not really go into detail about all the requirements for the certificates, also not for freshwater and seawater. What is important though to mention here is that these certificates will not be granted to final products that do not have a function in these environments. So for instance, a drinking straw or something will never be able to certify with these for these certificates. So again, the idea is we don't want to promote littering. Opportunities, of course, for these environments, really products that are used in these environments, like fishing nets, like mulch films, like control release fertilizers. It's really an added value if these would also be biodegradable in these environments. But also, there are a lot of products that maybe do not have a function in these environments, but will end up there through usage. Because, for instance, if you think about the fibers of your clothes, if you wash them, they will end up in the environment. And here it would really be a benefit or an added value if they would be non-persistent. So let's think about shoes, but maybe also like car tires, balloons, etc. So also maybe here, the biodegradability should not be discussed from like a business to customer perspective, but maybe from business to business, it could be something that could be discussed. Also, the certificates have time frames in which biodegradation should be reached, and maybe for these products, this short time frame in which you should obtain biodegradation is maybe not critical. Maybe we can allow for a longer period in order to biodegrade, because what we want for these products, these non-persistent products, is that not that they biodegrade fast, but that they eventually do not accumulate in the environment. So biodegradation. So Maarten already explained what biodegradation is. Basically, this breakdown of organic matter by these microorganisms. And what we measure in the biodegradation tests that we perform is the CO2 production, or of course also methane production in case it's an anaerobic test. So it was already discussed that biodegradation is, of course, the environment is critical for biodegradation. So the environment determines the degree of biodegradation, but also the rate. So if you look, for instance, the first graph is industrial compostability, we see that PLA and PBS, they are biodegradable under these conditions. If you look at the second graph, which is soil, you see that PBS and PLA are not biodegradable anymore. So really the environment determines the degree of biodegradation. If we then also look in the first graph to PCl, as you see, it biodegrades faster than PHB. In the second graph, in soil, it is somewhat slower. So, so the rate is also depending on the environment. So this is a poster that OWS created with some partners, and it's to show that the environment determines the degree of biodegradation. So if you look at cellulose, for instance, it's a very easily biodegradable material. We see that it's biodegradable in all environments. PBAT, for instance, biodegradable under industrial composting conditions, but for home and soil, it has been proven for certain grades. PLA then, biodegradable under industrial and also under thermophilic anaerobic conditions. This is because PLA really needs this thermal trigger for the hydrolysis, and only then the biodegradation can actually take place. So therefore, this thermal trigger is really important, and the temperature is high in industrial composting facilities, but not in home composting, soil, etc. Of course, I was talking about standard PLA, but there is also research being done to tune this biodegradation. So for instance, by blending or by enzymes. And this is a project in which they wanted to tune the biodegradation of PLA by making blends. So this is for industrial compostability. So you have the blends with PLA, PCl, PBS, PHB. And then what you see, if you look at home composting, that the PLA and PCl blend actually also was home compostable. The other ones, so PLA with PBS and PHB, did not work. So basically, by making a blend, you can tune this biodegradability of PLA. So then they looked in BioNTop, they looked at these blends, but also at the concentration of these blends. So in the first graph, you can see they made blends of this PLA and PCl, and in the second, it's PLA with PBSA. And they changed the concentration. And what you can see here, which is really interesting, is that the degree of biodegradation is not really changed that much in most cases, or in most cases, it will go to the same level of biodegradation. But the rate is really depending on this concentration range. So for instance, here you see that this 80-20 PLA PCl blend really goes quite quickly to this plateau, while the 95 with 5% PLA PCl, it takes a much longer time. And this, of course, can be interesting or for opportunities like you can maybe mix with the concentrations, with the ratios, depending on the application of your product and how fast a product needs to be biodegradable. So then a little bit on Champion. So Champion is it's a European project, and what you have, it's about polymeric materials used in adhesives, coatings, home care, and these are often fossil-based. Also, there are some toxicity issues, and they are due to they're not biodegradable, but also due to their usage, they end up in environment. You cannot recycle them. They, due to wear off, etc., they end up in the environment. So because of this accumulation, to ensure that they do not accumulate in the environment, the goal of Champion project is actually to look to these polymeric materials, to create new polymeric materials that are bio-based, and that are recyclable and degradable. And also, they also are looking at environmental, so safe by design, also to the environmental safety. And the goal is really to create novel-based and high-performance materials. And they do it through the aza-Michael addition chemistry. So you have these unsaturated polyesters, which do not have the functionality, and then you have the amines that you actually bind to create functional final materials. So what we saw, OWS was a partner is a partner in this European project. What we do is we actually do the tests on the biodegradability, so to determine the biodegradability. And what we did here is soil biodegradation testing, but at a higher temperature, so 37 compared to 25 degrees Celsius, to have accelerated results. So what you see, conventional products, they are high in performance, but they are not biodegradable. So limited biodegradation. And with the functionalization of these amines, you actually have a decrease in biodegradability. But here, so what you can see on the graph is that you have these unsaturated polyesters. So they do not have the functionality, but they are biodegradable. And then you have the dark green line, which are the conventional radical cross-linked materials. So they have the functionality, but they are not biodegradable. And in the Champion project, they made cross-link. So when you cross-link the amines, you get improved biodegradation over this conventional radical cross-linked products. So through this aza-Michael chemistry, they cross-linked amines to these unsaturated polyesters, and had increased biodegradation results. The testing on the functionality is still ongoing, so I cannot really share anything about that. But yeah, so that's interesting, and further research will be done on this. So this was my presentation. Thank you for listening.
Thank you very much, Astrid, for this clear presentation with a lot of details. We will continue this webinar series in November. We have the data still to be announced. The topic that is foreseen for the next webinar is toxicological safety of bio-based products. To hear about the date of this and future webinars, sign up for the Champion newsletter or just email us. All this information you can find on our website, champion project.eu. You can also see it on the slide.